Okay, we are going to look today at polynomial inequalities, and then this section also includes rational inequalities, but rational inequalities are just like, there's like one little step that you have to do in addition to what you do for polynomial inequalities. So if you can wrap your brain around polynomial inequalities, you're like 95% there for this section, okay? So we want to compare these two polynomials here, right? We have polynomial on the left, third degree polynomial on the left, and a 0 degree polynomial on the right. We want to know, when is this polynomial less than 15? So when we ask that, we're really asking for what x values is the thing on the left smaller than 15, which is the thing on the right. Okay, so from a graphical standpoint, this is what we're looking at, right? This red line, that's at a height of 15. That's y equals 15. And here is this blue curve is the other thing, the x cubed plus 3x squared minus 13. And we want to know, what are the x values that give us the blue curve below the red line? And what are the intervals that give us the blue curve above the red line, right? That's really what we're asking about when we ask about inequalities. For what x values is this polynomial less than this other one? And there are numerous reasons why we can't do the traditional algebra that we're used to with like linear equations and quadratic equations. Why can't we just use that for inequalities? And there's a number of different reasons why things just don't work the same, right? Think about the fact that when you divide by a negative, that inequality switches around. You don't have to worry about that when you're dealing with equations, right? So we have to have a different way of solving these inequalities. So we looked here at the blue curve and the red line. Well, I want to show you something. What if we said, you know, one of the things we do when we're solving an equation is we try to get 0 on one side of that equation, right? That's a very common thing for us to do. Well, what if we tried to do that here with an inequality? Would that be a good idea or a bad idea? And the answer is, it's a pretty good idea. It's going to make things easier for us to do. So what I'm going to do is subtract 15 from both sides of this inequality, and then we get this one, which is a little bit easier to deal with because now we have a polynomial on the left that we are comparing with 0 on the right. It's a little easier to compare things to 0 than it is to compare them to 15. And let's look at this graphically. See the places where the curve is crossing, the blue curve is crossing the red line? Well, now look at our new version of our polynomial, which the green polynomial is the one where we subtracted 15. It's this thing right here, right? This piece. That's the new green curve that we're looking at. And sure enough, if you look at it, it sure looks like the places where the blue curve crosses the red line also looks like the same x values where our green curve crosses the x-axis, right? And right here, they cross right here, and if we go straight down, yep, that appears to be an x-intercept. And the same thing over here. In other words, this green curve that we came up with captures the same information as the blue and red curves together, but just dealing with the green curve is going to be simpler because we have one function to deal with instead of two, right? So instead of dealing with those, we're now just going to deal with the green curve. So that's what justifies this, right? The subtraction of 15 from both sides. Now, how do we actually go about dealing with this? Well, the first thing we're going to do is we're just momentarily going to pretend like it's an equation, right? Ultimately, we have to answer this problem in the form of an inequality, but we are momentarily going to pretend like it's an equation. And here's why. We want these x-intercepts right here. Why do we want those x-intercepts? Well, if you think about it, what we're trying to do in this problem is break up our function into the places where it's negative, that is, the y values are below the x-axis, and the places where it's positive, the y values are above the x-axis. Well, where does that happen? Well, it happens right at the x-intercepts is where those changes occur, right? Right at the x-axis, we go from being negative y values to positive y values. Here, positive y values to negative y values. So they're changing, okay? Those happen at an x-intercept. And this is guaranteed to happen by the intermediate value theorem, right? Remember, that's in your book. So the intermediate value theorem basically states if we have a continuous function, and polynomials are continuous functions, but if we have a continuous function and it has y values of different signs, then in between those two y values, there has to be an x-intercept, right? Just like over here. If we go from this negative region to this positive region, well, somewhere in between there had to be an x-intercept. The same thing here. To go from positive to negative, well, in between there had to be an x-intercept. So intermediate value theorem guarantees that, we're going to get those x-intercepts. And that's the things that break up basically those intervals are going to break up our region into an area where the function is negative and where it's positive. Okay. So that's like, from a conceptual standpoint, that's where we're going. So we want to go ahead and keep solving this equation here. So this problem is factorable, so I'm going to go ahead and factor it. Right? So we have it in factored form. Then we can go through and we can solve it, and we're going to get x equals 3, x equals -1, x equals -5. And sure enough, if we look at the graph, let's see. Looks like these are, looks like we're getting an x-intercept at -5, -1, 3. So it's not coincidence that it's the same values we just solved for in the equation, right here. So these were giving us the x-intercepts. So basically what that's done, if you think about it, those x values of -5, -1, and 3 have broken up our polynomial into intervals over whether each of those segments by itself, the y values are either always positive or always negative. Like if we break it up here, as for any x values bigger than 3, your y values are going to be positive. For any x values between -1 and 3, your y values are going to be negative, right? So see how they're consistent throughout that interval? Now, I'm cheating a little bit by showing you the graph because you could just look at it and figure out where it's positive or negative. We want to be able to do this algebraically. The reason I'm showing you this graph is so that you can understand conceptually what we're doing, right? You're not just memorizing it. You understand what's going on. But keep in mind, like normally you don't have the graph there helping you. Okay, so then what we do is we are going to pick test values that occur in between these x-intercepts. So we know that that everything between -5 and -1, the y values are all going to have the same size. But we don't necessarily know, if we're not looking at the graph, if they're positive or negative. So how do you figure out what it is? And the answer is you just test a value. You just pick a value that's an x value that's in this region. You plug it into your function, and do you get back something that's positive or negative? And we make a little chart out of it. It's called a sign chart. A lot of people try to do this kind of problem without the sign chart. They try to skip the sign chart, and I can tell you it's not a good idea. Okay, it generally doesn't go well at all. And for those of you that are calculus bound, you're going to make a lot of sign charts. So you need to be good at them because you're going to have to be able to do it. So don't try to work around and think, oh, I can just answer this question by kind of looking at the graph. Don't do that. That's sort of defeating the whole purpose. Like the purpose of this section is to be able to write good sign charts because those of you going to calculus, you need to be able to do that. So don't try to skip that part because that's actually the whole point, is being able to make those. Okay, so our sign chart will look like the following. Well, we're going to do some test values. Well, yeah, let's look at our sign chart. So here's what our sign chart looks like. So notice I've broken the x-axis up into the intervals that are defined by those x-intercepts that we came up with, right? -5, -1, and 3. So these are all the intervals that go between those x-intercepts. Now, imagine this isn't over here yet. It's kind of filled in, but you might be wondering, how did he get those? How did he know that this one's negative and this one's positive? Well, we haven't actually done that part yet. So let's go back up to but I just wanted to motivate what we're doing. So let's go back up here. We're going to choose some test values, and we're going to pick an interval. Pick whichever interval you want here. You're going to have to do all 4 eventually, but pick whatever interval you want. And you just pick a value that's inside. So in other words, from -5 to -1, this interval from -5 to -1, just pick any value in there that you like. Okay, how about -2? -2 is in this interval. So I'm going to take -2 and I'm going to plug it into my function f. So, this is just the polynomial being evaluated at -2. And we don't actually even care what the number is. We only care about the sign of that number. So when you simplify all this, you get something that's greater than 0. So that means the y values on this interval from -5 to -1 are positive. Okay, so then we just go down to our sign chart, and next to -5 to -1, we put a plus, because that means all the y values there are going to be positive. Okay, now let's pick another test value. So this time on the interval from -1 to 3, we want to pick something that's in this interval. And you know what? Especially when it comes to polynomials, 0 is a great value to pick. Okay, so on the interval from -1 to 3, let's pick 0. 0 is really convenient to plug into polynomials because everything goes away except for the last term, which is -15, which is less than 0. So we know the y values are all negative over that interval. So we go down here, and from -1 to 3, we put a negative in there. Okay. Now the other two, you would just go pick a test point that's somewhere in this interval. See if you get positive or negative values. You will get negative values. Then take a test point from 3 to infinity and test your value there, right? And we can kind of verify this. Yep, it looks like from -infinity to -5, our y values are negative. From -5 to -1, our y values are positive. So we can verify it by looking at the graph that this sign chart is telling us where the function is positive and where the function is negative. Now, how do we actually answer the question, right? Because the sign chart is not our answer. We use our sign chart to give the answer. So let's go back and remind ourselves. What was the original question? The original question is, when is this polynomial less than 15? And we converted it to, when is this polynomial less than 0? And we said those happen in the same places. So now let's see. So we want what, less than 0? That means we're looking for negative values. So we go down to our sign chart and say, where does it have negative values? Well, that would be from -infinity to -5 and from -1 to 3. So this polynomial, this cubic, is less than 15 when your x value is from -infinity to -5 or from -1 to 3. And that's how you do that problem. Okay? The polynomial problems will all basically work like that. Now, couple things I want to point out. The only real difference that you do for rational inequalities when you're doing this is, remember, we use the x-intercepts to figure out the intervals for our sign chart right here. Well, when you're doing a rational function, you're going to do that, but you're also going to throw in any undefined points that you have. So your intervals for the rational functions will be defined on the x-intercepts, just like it was for polynomials, but also on any undefined points, like where you have vertical asymptotes. You're gonna divide the x-axis up on those points as well. So it's largely the same procedure.